Welcome to the video lecture of UPH 004 Applied Physics course. In this video lecture, we'll cover section optics and we'll talk about interference. The topics that we will cover are parallel and wedge-shaped thin films, how the interference happens in parallel and wedge-shaped thin films, what are the conditions for fringes, different properties of the wedge-shaped thin films. Then we'll talk about Newton's rings. Then we'll talk about some application of the interference pattern on the wedge-shaped thin films and parallel thin films and how that helps us creating non-reflecting coating. Then we'll talk about measurement of wavelength and diffractive index using the Newton's rings method. With this, let's start with the video lecture itself now. In this part, as we are looking at the interference due to parallel thin films, let us now look at some of the examples of the interference patterns and fringes that you see in nature due to the interference at a parallel or a wedge-shaped thin film. So here there are several examples where you see nice, vibrant, multicolored patches around in different parts of here it's a snake, here it's a peacock, here it's a butterfly, here is a fly, here is a splash of petroleum oil on a surface, here is a beetle, here is the surface of a fish tank. So in all cases what is happening is basically there are thin films over some surfaces, and when light falls and reflects back from those thin films, then the light interferes and creates this nice color. First we'll look into the phenomena of this interference in case of a very ideal case, a parallel thin film where the thickness of the film doesn't change, and in the next case we'll consider a thin film where the thickness gradually changes from one side to the another side. So that those are called edge-shaped thin films. Next, so to understand the interference, first look at what are the conditions of interference. So of course, for interference you need more than one light beams or rays to meet at one particular point where the interference will occur. But the interference that we talk about in the normal sense, there are certain conditions on the sources of the light which must maintain to see a nice interference pattern. For any two light, if they meet at some point, they will interfere. But whether you will see a nice pattern or not, that depends on these conditions. So first of the condition is that the light source must be coherent. So what do we mean by a coherent source? If two sources are such that the light coming out of those two sources maintain a constant phase relationship. So it doesn't matter whether it's the phase relationship or the phase difference between the two rays is zero or non-zero value, but that whatever the value is, that should remain constant. Now there are two types of such coherence. One is called temporal coherence and another is called the spatial coherence. What is the temporal coherence? Temporal coherence is that the phase difference or the phase relationship doesn't change if you measure the phases at different times. And spatial coherence means the coherence or the phase relationship that remains constant or that is preserved in space. So if you measure the phase relationship at two different points in space, then the phase difference doesn't change. So spatial coherence and temporal coherence, of course, they are not independent quantity. If we know one very well for two sources, whether their temporal coherence is maintained, then in that case we'll be able to know what would be the spatial coherence. So that was the first condition here. For two rays to interfere, they must be coherent. So that's rule number one or condition number one. The second condition is that the light must be monochromatic. What do I mean by the light must be monochromatic? So the two beams those which are interfering must have the same wavelength. And the last one is the principle of superposition must apply. So what is the principle of superposition? It's just simple. So in a mathematical sense, if there are two sources and let's say the light from one source is E1, from the another source is E2, So here is a source, here is a source, the light is going from here and they are meeting at one particular point. And so here it's E1, here it's E2, and let's say the final light is E12 and that must be E1 plus. So this is called superposition principle, that the resultant is always a vector sum of the lights which are meeting at that point. So this condition must be satisfied. So these are the three conditions for the interference.